The Earth is a remarkable piece of real estate and a busy one at that. From its ever-changing weather patterns to the hustle and bustle of city streets, our planet is constantly in the state of motion. However, if we look just below the surface, we can find that things are also moving below our feet. This is called plate tectonics, and it's how the continents are formed and reformed. When one looks at the map of the continents of the world, it is tempting to speculate that the Atlantic coast of Africa and those of North America and South America could fit nicely together as though they were pieces of a jigsaw puzzle. This observation has led scientists at various times to suggest that these continents, and perhaps the other continents, were once a single giant supercontinent that broke into large fragments called plates and then drifted apart. However, scientists had no evidence to support the idea of such an event other than the shapes of the continents. In the early 1900s, Alfred Wegener, a German meteorologist and geophysicist, revived the idea of plates and their movement and assembled various types of geologic evidence supporting the model known as continental drift. Wegener's hypothesis gave rise to considerable controversy, and only in the last few decades has conclusive evidence been found out that supports some aspects of it. Today, continental drift is a well-known tested theory. Wegener's assumption was that the continents were once part of a single giant continent, which he called Pangaea. He proposed that this hypothetical supercontinent drifted or broke apart about 200 million years ago, and that its sections somehow drifted to their present positions and became today's continents. The scientific evidence supporting Wegener's hypothesis that the continents once formed a single landmass is of several different types. Let's briefly consider the three most prominent. First, biological evidence. Similarities in biological species and fossils found on distant continents that are today separated by oceans strongly suggest that these land masses were at one time together as Pangaea. For example, fossils of identical reptiles have been found in South America and Africa, and identical plant fossils have been found in South America, Africa, India, Australia, and Antarctica. Second, continuity of geologic features. The roughly interlocking shapes of the coastlines of the African and American continents inspired the theory of continental drift. Imagine the continental shapes to be interlocking jigsaw puzzle pieces. When the pieces are put back together, the fitted pieces display a continuity of geologic features. Third, glacial evidence. Solid geologic evidence confirms that a glacial ice sheet covered the southern parts of South America, Africa, India, and Australia about 300 million years ago, an ice sheet like the one that covers Antarctica today. A reasonable conclusion is that the southern portions of these continents were under the influence of a polar climate at that time. Wegener's hypothesis suggests an answer and derives support from these observations. The direction of the glacier flow is easily determined by marks of erosion on rock floors. If the continents were once grouped together, the deglaciation area was common to the various continents. Although this evidence supported Wegener's theory, it was not generally accepted primarily because he could not explain how continental crust could move through much denser oceanic crust. The mechanism behind continental drift was suggested in 1960 by Harry Hess, an American geologist. Geologists knew that at that time that a mid-ocean ridge system stretches through the major oceans of the world. In particular, the mid-Atlantic ridge runs along the center of the Atlantic Ocean between the continents. The East Pacific rise runs along the Pacific Ocean floor just west of the North and South American continents. Geologists also knew about the deep, narrow depressions that ring the Indian and Pacific Oceans, called deep sea trenches. They are the lowest places of the Earth's surface. Harry has suggested a theory of seafloor spreading, where the seafloor slowly spreads and moves sideways away from the mid-ocean ridges. Molten rock then wells up into the gap and cools to form new seafloor rock. Thus, the seafloor moves away from the ridges, cooling and contracting as it moves. When it reaches the trenches, it descends back into the mantle. A support for this theory has come from the studies of remnant magnetism and from the determination of ages of the rocks on each side of the mid-ocean ridges. Remnant magnetism is the magnetization of rocks that form in the presence of an external magnetic field. When molten material containing the mineral magnetite is extruded upward from the mantle, for example in a volcanic eruption, and solidifies in the Earth's magnetic field, it becomes permanently magnetized. The direction of the magnetization indicates the direction of the Earth's magnetic field at the time. Thus, the newly formed seafloor rock preserves the magnetic record at that time. These observations support the idea of seafloor spreading as mechanism for continental drift, an idea that has culminated in the modern theory of plate tectonics. Instead of continental crust plowing through the oceanic crust, it is now known that both are carried across the upper mantle as part of the lithosphere.